Welcome back to Integral Calculus. In this video, I want to introduce you to the hyperbolic function. The story of the hyperbolic functions starts with Euler's formula, which we saw previously. If you evaluate an exponential function at an imaginary value, you get this sequence of trig functions. Now that we've seen this, the interesting question becomes, what happens if we take the trig functions and evaluate at imaginary values? Well, to get there, the first thing we need to do is get a second exponential. If we take e to the opposite of I times x, then we would evaluate cosine at the opposite of x. Cosine is an even function, so cosine of the opposite of x is the same thing as cosine of x. Then we need sine of the opposite of x. Sine is an odd function, so sine of the opposite of x is the opposite of sine of x. That gives us this formula. Now, something interesting happens if I add or subtract these two equations. I'll subtract first. E to the ix minus e to the minus ix. Cosine of x minus cosine of x cancel each other out. Sine of x minus sine of x, those two negatives become an addition, and we get 2 times I times the sine of x. Or rearranging this, sine of x is e to the ix minus e to the minus ix all over 2I. If instead we add these things together, e to the ix plus e to the minus ix, I think this is a little bit more clear what's going to happen. We have cosine of x plus cosine of x, which is 2 cosine of x, and then we have sine x minus sine x, which is 0. So rearranging this, we get that cosine of x is e to the ix plus e to the minus ix all over 2. And it is these formulas that we are going to work on when we try to plug in imaginary values. So I want sine of ix, which would be e to the I times ix, so I squared x, minus e to the minus I squared x, all over 2I. A couple of interesting things happen here. I squared is -1, so that first exponent becomes e to the minus x, and in the second exponent we have the opposite of -1 times x, which is just x. And then the last thing that I'm going to do is rationalize this. I'm going to do that by multiplying top and bottom of this fraction by I. The I in the numerator I can bring in front. That's going to be a more convenient place for it. And then the I in the denominator times the I that was already in the denominator gives us -1. And now, because I have subtraction in the numerator and a negative in the denominator, I can bring those things together and write that sine of ix is e to the x minus e to the minus x over 2. The work for cosine is a little bit more straightforward just because we don't already have the I in the denominator. If I want to evaluate cosine of I times x, I'm going to get e to the I squared x plus e to the minus I squared x all over 2, which is e to the minus x plus e to the x all over 2. And then because it's addition in the numerator, I can just switch the order and write that as e to the x plus e to the minus x all over 2. These two expressions turn out to be useful in a number of places, some of which are kind of surprising. And so we're going to define what are called the hyperbolic functions. The hyperbolic functions, hyperbolic sine, sometimes called sinh, is going to be e to the x minus e to the minus x over 2. And hyperbolic cosine, sometimes pronounced cosh, is going to be e to the x plus e to the minus x over 2. So we can see where these things came from, and we can give the first set of identities, which is that the sine of ix is I times the sinh of x, and the cosine of ix is cosh of x. I tend to remember these as some sort of an extension on even and odd. Sine is an odd function, so when we try to take it for an imaginary value, we end up with an imaginary in front. Cosine is an even function, and it's, again, by coincidence, but it's helpful to remember. Put an I inside, that I gets eaten when we transform from the cosine to the cosh. There are other hyperbolic functions. Now that we have this inspiration of the sinh and the cosh, we can try to name the rest of the functions. The hyperbolic tangent, tanth of x, is sinh divided by cosh. The hyperbolic cotangent, the coth of x, is cosh divided by sinh. The hyperbolic secant, the sech of x, is 1 over the cosh. And the hyperbolic cosecant, the cosh of x, is 1 over the sinh. I've never seen an application for the other hyperbolic functions, but they do exist, and a lot of textbooks love to talk about them, so I felt like I had to at least mention them. Instead, I want to think a little bit about why we gave these the name of the hyperbolic functions. So going back to sine of ix is I times hyperbolic sine of x, and cosine of ix is the hyperbolic cosine of x. Well, remember that on the unit circle, we have ordered pairs x, y, where x is the cosine of theta and y is the sine of theta. And this is the unit circle, which gave us that cosine squared theta plus sine squared theta equals 1. But more to the point, this is the equation of a circle. X squared plus y squared equals 1. what happens if we try to evaluate this at imaginary points, at an imaginary angle? Cosine squared of I theta plus sine squared of I theta should still be equal to 1. Cosine squared of I theta is cosh squared of theta. Sine squared of I theta would be I squared times hyperbolic sine of theta. And I squared is -1. So instead of x plus y, this would give us x squared minus y squared equals 1 as the generic form. And if x squared plus y squared is 1, then x squared minus y squared is 1 is the equation of a hyperbola. Just a quick reminder for you, the unit circle x squared plus y squared equals 1 I have here graphed in blue. The unit hyperbola x squared minus y squared equals 1 I have graphed in orange. And this really is the relationship of hyperbolic functions. Take all of the rules that you have for dealing with a circle and getting cosine as the x component, sine as the y component, and move them to the hyperbola, getting cosh as the x component and sinh as the y component, and it all works the same way. That relationship is very literally why these are called the hyperbolic functions. They are what would happen to trig if you did it on a hyperbola instead of a circle. There are surprisingly a number of applications of this. We will get to some of those applications, but for right now, I just want to focus on what are these functions and how do they behave. Right, so let's get back to our notepad here. We already have several of the identities that we need, right? We have the ratio and reciprocal identities. We also have the equivalent of the Pythagorean identity, which looks incredibly similar. The last thing that I want to look at are the equivalents of the double angle identities. So just really quickly, remember that for the trig functions, sine of 2 theta is 2 times sine theta times cosine theta. And cosine of 2 theta, there's a couple of different forms that you can get using the various Pythagorean identities, but generally cosine squared theta minus sine squared theta. Now, if we try to look at the same expressions for sinh and cosh, the hyperbolic sign of 2x, using our definition, this would be e to the 2x minus e to the minus 2x all over 2. And now if I can be a little bit creative, I can think of e to the 2x as e to the x squared. And likewise, e to the minus 2x is e to the minus x squared. Just using the power to a power rule for exponents, usually the backwards of how you normally would think about it. But now I have this explicitly written as the difference of two perfect squares. So I can factor it. This is e to the x minus e to the minus x times e to the x plus e to the minus x all over 2. If I'm really careful about this, you might notice that it would be really nice if I could take e to the x minus e to the minus x over 2 and also take e to the x plus e to the minus x over 2, which introduced an extra factor of 2 in the denominator compared to what was there before. But I can fix that by putting a 2 out front. Why was this useful? Well, because that first fraction is the definition of hyperbolic sine, and the second fraction is the definition of hyperbolic cosine. So just like sine of 2x is 2 sine x cosine x, sinh of 2x is 2 sinh x cosh x. The double angle formula seems to work exactly the same. This one's a little bit trickier. I'm not going to go through the algebra because I don't think it's worth the time. But following a similar procedure, you will eventually end up with the cosh of 2x is cosh squared of x plus sinh squared of x. So a difference of addition instead of subtraction, but the same basic idea. Now that I've gone through all of the hard parts of the hyperbolic functions, I'm going to let you work through some of the easy parts. Make sure that you are comfortable enough with these formulas that you can use them to evaluate things. How about the cosh of 2 and the hyperbolic sine of pi over 4? Take a couple of minutes, work through those evaluations, make sure that they make sense, and I'll see you in the next video.